Okay, so despite the title, I'm actually going to tell you about something very specific related to this, which I should write is basically joint work with Samek Basu and Debasis Sen, but it's also based on earlier stuff with Hans Bauer, Mark Johnson, and Jim Turner. And there is a connection to Paul that I'll come to at a later stage. So I guess nowadays everyone talks all the time about infinity categories and, or the way I like to think of them as simplicially enriched categories, which are very nice for a lot of purposes, but part of the problem is because they're these infinite structures, it's very hard to actually extract information from them. So one point that is obvious, and I think has been made here several times, is that if we're thinking of these things as simplicially or topologically enriched, then we can approximate the full structure by taking Postnikov sections. So we both have nth order approximations for AVN, and they're related by Postnikov towers. In fact, we even can have K invariants for them if you have a simplicity enriched category. But that doesn't really get us very much further on the way to what we'd really like, which is to be able to sit down and hopefully calculate, or if not calculate, at least exhibit some higher order structure. So of course we know that if we just take pi 0 of these mapping spaces, we're going to get the homotopy category, and that's hopefully where our homotopy invariants live. Some of them are just visible in the homotopy category, such as homotopy groups or cohomology groups, but well, we had many examples of invariants. Maybe the most familiar is differentials in spectral sequences, or the total brackets that Tyler was telling us about, and yeah, all over the place, all these AN structures and so on. They're not, the answer is a homotopy invariant, but they're not visible, and you can't even define what you mean in the homotopy category itself. Okay, but this idea of approximation tells us that we can talk about nth order invariants rather than just saying higher invariants, and those are the ones that should be visible, or we can extract them somehow from the nth Postnikov section, or the truncation, if you'd like, of the enrichment. Okay, so that gives us some handle on what we were talking about, but it doesn't really get us anywhere further in actually getting our hands on these things. And so what we'd like is some notion of higher structure, or more specifically, nth order structure that we can work with in some way, and a way to extract from that higher order invariance. So I don't pretend to have some general method that will work in all cases, but I think that if I describe a certain example, which I'll get to in a minute, it might help you see what kind of things we might want to have and how they work in a specific example, which is related to the unstable atom spectral sequence, or in fact also to the stable classical atom spectral sequence. Okay, so one other general point that I should point out is that if you think of a simplicial enrichment, in, say, we can think of everything happening in topological spaces. That's as good as we want. So in dimension n, what we have here are actually Hom, if you'd like, and this works in many situations, from delta n into y. So, okay, this suggests that the kind of things we're looking at up to dimension n, and certainly in the n Postnikov section of this, has at the very bottom maps, and then homotopies and higher homotopies. Okay, that's the theory behind it. to actually give, even if you want a model for these things, there are models for n types of spaces, or and in particular, of course, in these cases, we're interested in spaces which are not connected, because the components are obviously relevant here. There are models for those things, but those are really, really complicated, and in some sense, these kind of n category models that we have are even more complicated than infinity categories, in the same sense that things at the prime 2 are more complicated than things at an arbitrary high prime. If you actually need to look at the details, it becomes a little messier. But one thing that we do, that we can see in this setting, is that there is a correspondence. If you just think of things like the nerve or coherent nerve of a category, there is a correspondence between what we see here in dimension n and certain diagrams, and diagrams typically of length n, in the sense that we have a sequence of arrows of length n plus 1, whatever, that are encoded in the n simplices of something like this. Or maybe that's more visible in other models for infinity categories. So I think as a general slogan, what I'm proposing as the notion of a higher structure here is that we are forced to look into this something I call an n category version, something where we actually get our hands on something, but we try to do that as little as possible and move over as quickly as we can into looking at diagram categories, because I think I don't know if it's a folk theorem, or there are certainly instances of this that are well known, that if you look at all possible diagrams, say, of topological spaces, and just look at their homotopy categories, but take into account the various functions between them, restrictions and all the things that we have, that also encodes certainly the same information as we get in the mapping spaces. So, and of course, model categories are a much easier thing to work with. We can't actually get our hands on things, but it's easier to say, okay, we apply a functor to this, we do various things. If you like, you can think of them as a black box, and we open it up a little bit to look inside and extract the information that we need, and then move back into the diagram. Okay, so maybe that's as far as I want to talk about general higher order structure. And now I want to look at this specific example of the unstable Adams circle sequence. So let's start first with the notion of p-completions. So now let's say Y will be a p-good, simply connected, finite type, whatever. It doesn't, we're not talking about the problems that, I forget who it was, Anne-Marie mentioned, that arise in this situation, but just the basic simplest case that we have of a pointed, we have an pointed space. And let's remember a minute how we construct the p-completion of this space. So the idea is that the p-completion is supposed to tell us what is visible to mod p cohomology. And in particular, if you think a little further, it's what's visible if you map this into p-gems, in other words, products of mod p Allenberg-MacLane spaces. And the other side of it is that we want them somehow to be built out of such spaces. So we want to build an approximation to Y, which is constructed out of these p-gems and reflects all the information that they can see. Okay, so let me just remind you. So the construction of the p-completion of Y is we start with Y, we form a co-simplicial resolution of it, in which each of these spaces is one of these p-gems. So resolution in the sense that when you apply cohomology, it'll be a resolution in the ordinary sense of the simplicial object you get is acyclic. And then we take the total space of this, which was also mentioned in one of the earlier talks, and that will be the p-completion. Okay, and what Bousfield-Kahn, if those of you who have looked at it, gave a specific construction, but Bousfield later on said you can actually use any resolution in this suitable resolution model category of cosimplicial spaces. So how do we look at this question from, well, we want to do two things. On the one hand, we want to think of this successive approximations and construct this by successive steps in such a way that we'll have this kind of higher structure that I mentioned before, or we'll make it visible. Okay, so the first thing that we do, and we start from the 0th approximation, which, by what I said before, is what's visible in the 0th Postnikov's section of these mapping spaces, in other words, in the homotopy category. So what do we know in the homotopy category? We're mapping into these p-gems. We're going to get simply the cohomology of Y, but we're allowed to compare different p-gems, so we actually get the cohomology of Y as an unstable algebra over the Steiner algebra. So let's say that we'll call this gamma will be the cohomology of Y as an unstable algebra over the Steiner algebra. Okay, now, so this is a perfectly good category. It's not abelian, but we can do resolutions in this category. So that's what we would say. So what, in fact, we have to, what the Bousfield's definition of a resolution, aside from each of these being a p-gem, is that when we apply cohomology, as we said, we will see, we'll get a resolution of the cohomology of Y. So here is gamma, and a prerequisite for constructing this is that we have some resolution of the cohomology after applying mapping into these algebraic spaces. Okay, now let's think a minute how we construct that, because we want to, as I said, we're trying to kind of alternate between this idea that we have the Postnikov sections here and the idea that we have longer and longer diagrams, and they're supposed to correspond to each other. I'm not going to go into all the kind of circle of ideas that we can get to do that. I just want to stick with the stuff that's relevant to this idea of higher invariance. Okay, so let's think how we would go about constructing a resolution. I'm doing this unstably just because I want to have something completely firm to have our hands on. Actual spaces, actual maps between them, and not have to worry about models for spectra and what exactly is going on. But you can do versions of this stably if you prefer, but let's stick with spaces. And everything that I'm saying in the end, in the connection with the atom spectral sequence, you can just, since let's say if we're talking about a differential, if you just, and we're talking, let's say, about the homotopy groups of an actual space, you can just suspend it for far enough and look in the stable range, and then you would just be calculating the same differential in the stable atom spectral sequence. Okay, so how do we go about constructing a resolution? Let's say that we didn't have to realize it in this way by a cosimplicial space. We just want a simplicial resolution. Remember, we're changing direction because cohomology is contravariant. So we start with this gamma, and we can do it just the way you did resolutions when you first heard about homological algebra. We start with some free algebra over the Steiner algebra. Let's call that V0. We look at the kernel of this thing over here. So we have some augmentation here. We map onto this, and now we start running into trouble because we're not in an abelian category, so you can't just do a chain complex resolution. You have to do a simplicial resolution. You now have to take the degeneracies of these up here and look at things coming from the fact that it's algebras rather than modules of the standard algebra. So those mix in and we can get, okay, so there is a construction. Now let's just try and think how you would nevertheless describe a resolution in the way we're used to from homological algebra. Well, what I can do is, so let's say assume that we have a resolution, let's call it skeleton n-1, let's say, of V dot. So we're trying to construct a simplicial resolution, V dot, and let's assume we have it as through simplicial dimension n-1. Well, what we can do is look at what the Moore chains, which I hope are, I'll remind you in a minute what they are. I can write them as the Moore chains of V dot itself because that only depends on the n-1 skeleton. So secretly we have a skeleton n-1 over here. But I have the Moore chains, and what are these? It's simply the intersection I equals 1 to n-1 of the kernel of the face maps that we have here. These are the maps of algebras. The kernel is, again, a map of algebra. This is an algebra over the standard algebra. And all I have to do is take a map. Well, what I really want to do is look at the Moore cycles inside here, which is, here you notice that I started from I equals 1, so I still have the d0 left over as the differential. I take the kernel of that, and that will be the n-1 cycles. I simply have to choose a v bar n, which maps onto this, and I get a map into here. Fine. Now, we can think of that, if you'd like, in the language of chain complexes. I can think of this as a map from a chain complex of algebra. So even though they keep telling us you're not allowed to work with chain complexes, you can actually work with chain complexes here. You don't have the right model category, but you can do that. So I have a chain complex with this algebra. So this is kind of kicked up into dimension n-1 as a chain complex, and this map over here, which we think of, so we think of this as a kind of a CW complex. This is the CW basis. Here is the attaching map, and I've glued this on, and I get the next stage up. How you actually do that is not important. It's just a combinatorial exercise. Okay, but we can think of this as a map, which I will call, I guess, Vn, an attaching map, not just from one algebra to another, but actually into the full, and now I guess I should say, the full Moore chain complex. So this is a chain complex. You check from the simplicial identities that this is actually going to be a chain complex. D0 composed with D0 is going to be 0. So I have a map of chain complexes from one to another. Okay, so now what we're trying to do is realize this at the level of cosimplicial spaces. So it turns out, so now we assume, so we've assumed this. This is what we do algebraically, and we can continue indefinitely, right? Because there's no reason why we can't construct a resolution like this. However, a full algebraic resolution, simplicial resolution of this gamma, which is the cohomology of Y. Okay, so we now have it, and we have this particular CW structure on it, which, by the way, any resolution you have, you can extract, you can choose a CW basis, so to speak, for it. Okay, now let's try and realize this. So let's assume we have realized this n-1 skeleton of V dot, which we have all the way up, by a cosimplicial space, which I'll call W. So remember, it's contravariant, so this is now cosimplicial. I'll put an n-1 down here to remind us that it corresponds to the n-1 skeleton. And okay, I need it to be really cofibrant. So here is the point where the model categories come in. But okay, and then if that's true, then I get from that the Moore cochains on this, which is just dual to this, instead of taking the intersection of the kernels, you mod out by the image of the coface maps, that the Moore cochains on on this thing over here are going to have, well, okay, so this is something whose, when you take its cohomology, it's going to give you the thing that we had back here. I'm not going to write that down, but okay, I will write it down. Cohomology of this is going to be the more chains of v dot, which of course, when I say that we realize that, I mean that the cohomology of this gives us the v dot through the appropriate dimension. Okay, so now can we now realize this map at the level of chain complexes in spaces? So what does that mean? Well, we can try to do, of course, the direction of the arrows change. So I can try and map Cn minus 1 w dot. So this is not, yeah, this is true in general, up to the appropriate dimension. And now I can try to map this, which we said is the dual for what we had over there. I want to map that into w bar n. And this is something with a pgem which realizing v bar, sorry, that should be an upper n. This is in spaces. And I can, of course, this is a free algebra of the standard algebra, so I can realize it by some product of Weinberg-MacLane spaces. Okay, but now is this a map of chain complexes in spaces? So here I have Cn minus 2 of w dot, and I have the differential which is induced by the d0. And here I have nothing because, right, remember the original thing was just that concentrated in dimension n minus 1. So, okay, let's call this map Fn minus 1. And we ask, is this map going to be 0? Because that's what we need in order for this to commute. And we see that there's no reason why it should. Right? Because what I was saying about cohomology commuting with cohomology commuting with cochains in this sense doesn't work for the cycles. It only works for the cohomology. So no, it doesn't commute in this way. But if we now think of this from a more model theoretic point of view, that makes sense because we're trying to map into, even though this thing is simply a cochain complex in spaces, and here we have a cochain complex in spaces, this one isn't fibrine, so there's no special reason why something that worked up to homotopy is going to work here. So how do we make it fibrant? We make it fibrant by, well, in like any, I forget, projective or injective model category structure on these cochains, I have to take the limit of everything that I have coming above. Remember that these are chain complexes, so I have to take the limit of that is w bar n, and I now have to, well, map, instead of mapping a point into this, which is what I had before, I map something contractible by a fibration into here. So the obvious choice is to take the path fibration. And now I say, oh, yes, now this does commute because all I'm talking about here is a null homotopy for this composite, and the composite is null homotopic because after we apply cohomology, I see that that composite is actually 0 because it landed in here. Okay, so I have an Fn minus 2. Okay, now bear with me just 1 minute more, and we'll see what's going on here. So I want to continue this process. Let's see what happens when I try to continue this process. So let's say that I got to here, I have in dimension k plus 1 of w dot, and I guess all these should have an n minus 1 here, but I won't write that out all the time. So I have something here in fk plus 1, and now you do the math, and you see that what you have here is each time. So what will the next one after this, the fiber of this is loops on w bar n, but then I need something contractible mapping onto that, so it's paths on loops on w bar n, and so on. So in general, well, I'm almost more or less guessing, I think this will be something like this, w bar n. And here I have ckw bar n of this thing, and here I have fk, and this will be looped once more. So n minus k minus 2 of w bar n. And I'm assuming that this thing commutes. And now I come in with ck minus 1 of w dot. And I say, well, what do I know about this? If I go all the way up, this is just two successive maps in a cochain complex. So this is 0. So going like this is 0. So going like this is 0. But this map actually factors by first the path fibration to loops on n minus k minus 2, and then the inclusion into here. So if by the time I've gotten into here it's 0, this was a inclusion, so it's 0 also over here, therefore it factors through the fiber of this, right? This map is 0, so it factors through the fiber, minus 1 of W bar. Okay, now this is the critical point. What we've actually done here, if you remember Tyler's talk, is construct an n minus k minus 1 order homotopy operation. We've fit together a collection of things which are really just null homotopies of various composites of the original map. And we landed in, we've kicked it down n minus k minus 1 times from the original target at the very top, which is the W bar n. It turns out that this, because what we started with was a resolution, this map, so I'll call this thing AK, let's say AK minus 1, this thing always is going to be null homotopic. So I can lift it up to the next stage up, which is in fact exactly the thing that I wanted. So here I'm going to get an FK minus 1. And I can proceed in this way. Yeah, of course, as usual in these things, if I made a bad choice for the null homotopy, when I go to the next stage, it won't work, so I correct it, and finally, you can make it work all the way up. So what do we get out of this thing here? What we got is a map of co-chain complexes from this, the Moore co-chains on the approximation we had, simply a map into this thing which I'll call, let's say, D star. So this is a co-chain complex which is basically just W bar n in dimension n and 0 everywhere else. But I have a fibrant model for that. Okay, so what I'm claiming is that this map F, or more precisely this sequence of choices that we made over here, this is what I want to call the nth order structure for the P completion of Y. Okay, it's not ended yet because I now have to proceed and construct the next stage up. So remember, in chain complexes, what we did is we took the co-fiber of this map over here. So in co-chain complexes, but we were doing it actually we weren't taking the co-fiber of the map of chain complexes. We kicked it up to a map of simplicial objects because this is adjoint to adding well, basically this is adjoint to just enriching this to a full simplicial object by taking 0 face maps elsewhere and adding the degeneracies and so on. So once I have this, I get the map there, and I can take the co-fiber of that. And since we're doing it in the dual world, we now want to construct the fiber of this map F. Now notice that even though we made this fiber, and I wasn't requiring this map F to be a fibration, because from this stage on, we're going to do precise, we're just going to apply functors to things. Doesn't have to be homotopy meaningful. All the homotopy we have is encoded in this map that we have here. So I don't have to change this into a fibration. I have this actual construction. And it turns out that it's convenient to take, so I want to take the co-fiber of an adjoint of this, and it's convenient just to make it easier to draw on the board, to think of this as a restricted co-simplicial object. So I'm going to forget about the co-degeneracies and just put in the co-face maps to this. And what will that look like? Well, what I'll have in each, so I'm going to call this thing, let's say W tilde n. So this is supposed to be my next approximation. And what I will have is something that looks like this. This will have whatever we had in the old space, and I just add on that appropriate thing. And if you think about how cones on chain complexes work, you know this is going to get kicked up 1. So this will be, instead of dimension k that, we'll have P of loops of n minus k minus 1 of W bar n. We'll have, of course, the same thing 1 dimension lower down. Here we want to have all the different co-face maps. Okay, here we had whatever we had. right? We're assuming that we had a full co-simplicial object over here. Here we have this thing which we're calling, I guess it's now n minus k, W bar n. And the map that we add here, this map the maps that we have here, if you also think about the example of chain complexes, will actually be the one-face co-face map. So that's map down path fibration and then inclusion of loops into paths. And we'll have the zero differential will be this map that we were calling fk minus 1. And all the other face maps into here, co-face maps into here will be 0. OK, it's not clear why we're interested in this thing here. What I'm telling you is that this, in fact, is essentially the next stage. I now have to add the codegeneracies. I have to make it really cofibrant. I didn't tell you why, but we need that. So that's the point where I'm leaving the hands-on world and moving into the black box world. Basically from this stage on, but this part I could exhibit to you because we'll need it in a minute. Fine, so the claim is that I can proceed in this way. I'll actually get really fibrations from W bar n going down to W bar dot n minus 1 and so on all the way down. And if we take the limit, which is the homotopy limit of these, and call that simply W dot, this will realize the original V dot that we have. So along the way, what we're getting here is a way of a hands-on way of realizing an actual algebraic resolution by a co-simplicial resolution. Okay, what is this good for? Well, one thing that we get is it turns out that if you now just apply tot to this tower, to each stage in the tower, you're going to get a tower of fibrations. And the homotopic spectral sequence of that is, from the E2 turn on, is the unstable atom spectral sequence. So if you like, you can think of this thing as being a kind of unstable atoms resolution. You can construct at will, and you choose an algebraic resolution, you can realize it, and so you can make small resolutions. And I don't know if that's, the only people here I know who ever tried to calculate something with an unstable atoms resolution is, I guess, Haynes and maybe Catherine Lesch. But OK, but there is something that you can do with this. That's not the point that I want to make. OK, so now, before we get to that, to the atom spectral sequence, I want to explain what this is good for. So this, I'm claiming this F is what I'm calling the higher structure. Now, of course, we made a lot of choices along the way here. So one thing we need to know is that it doesn't matter what choice you made. Any one of them will work equally well. Anything that I'm doing with one specific choice will work for any other choice. So what do I want to do with them? Let's first start with a simple example. So higher invariant. OK, so assume Z is another P-good space with the cohomology of Z isomorphic to this gamma, which remember was the cohomology of Y. Now, it's not clear from this picture. You understand, once you think about it, that I must somewhere have taken into account the existence of Y, because otherwise I would just be, right, I have an algebraic resolution, I would be claiming that you can realize it. That can't be true. So Y is coming in because at the bottom of this tower, these things are not really co-simplicial spaces. They're co-augmented co-simplicial spaces, and we use Y at the very bottom of the tower. That's part of the picture. So you need to make them work in that category, and Y has to be there in order for this to work. OK, but now we're taking something else, and we're trying to ask, well, maybe this W dot is also a resolution of Z in the same sense, in Bousfield sense. How can we check that out? Well, let's see. If we start, I didn't say how we start the process, but it's pretty clear that at the very bottom, as I said here, you simply choose a V bar 0, and W square bracket 0 will simply be the constant co-simplicial space on that W bar 0 that realizes this. So that you can certainly map, right? So that's just an algebraic MacLane space. If you can map Y into it, you can map Z into it because they have the same cohomology. So what we assume we have a co-augmentation. I guess I should really be writing it with something like an eta n minus 1 from z into w dot n minus 1. So it's true for n minus 1 equals 0. You can actually get it to work for n minus 1 equals 1. Let's assume that we have a co-augmentation realizing the augmentation that we have for the simplicial resolution. And now let's see, well, the picture is actually there, but let me just draw it again so we can see exactly what's happening. So here is W0 n minus 1. Here is W1 n minus 1 with the two co-phase maps. I'm leaving out all the co-degeneracies. And here is W2 n minus 1, which I don't actually need. And here is Z mapping in by this map eta n minus 1. So here everything does exactly what we want. And now what have we done? We've added on, here we have just some path on loops on, let's see, here it'll be n minus 1, n minus 2, n minus 3, I guess, of w bar n. And here we have this map going across, which it was the map that we were calling F1, but it doesn't matter. It's just the 0 coface map into here. And we say, OK, 0 coface map into here. By the time I've composed, so here is a co-simplicial identity, that this is the same as doing all iterated coface maps down from the co-augmentation are giving the same thing. So this composite is the same as doing D2. And we said the only differential coface maps we had into here were D0 and D1. So this composite all the way into here is 0. But we could have written that in the form, right? We have this map down, the path vibration, and the inclusion into here. So if this composite, so that's the same as going up by this thing that we're calling F0 into here. And this is the same as doing this. But if this is 0, by the time we've continued into here, sorry, what did I do wrong here in this picture? I knew I was spacing it out wrong. So here we have this little inclusion of the loops. And in here we have the paths on loops on n minus 2 of w bar n. And this is where the map went into here. So it was 0 into here, therefore it's 0 into here. Therefore it factors through the loops n minus, I'm doing something wrong with the numbering here. This one should have had, no, this should have been an n minus 1. Yeah, that's the inclusion into there. OK, so what I got is a map into here, which is just this A minus 1, the same AK that we were talking about here. But in this case, it's no longer true that this is necessarily 0. This is a value of a total bracket, and the n minus 1 here says it's a length n total bracket. So either it vanishes or it doesn't. If it doesn't vanish, then we have an obstruction to extending this, because what are we trying to do? We're trying to get a map. The thing that we're missing, we map into this, fine. We need a map that we could call f minus 1 into here, which is a null homotopy for this map over here. So here is an example of a homotopy invariant for the space. Now, of course, there are a lot of choices, and people have said several times that total brackets or higher operations are not well defined, so it depends on all the choices we have before. But it's just like any obstruction theory. You trace back all the possible choices you make, and you get something. And in the end, if every choice you made leaves you to something non-zero, then you can't co-augment this into this, and therefore you can't co-augment it into w dot n, and that's the end of the story. So here we have an obstruction theory in the form of higher homotopy invariants. And in this case, we see how you use the structure. So the structure is, as I said, the collection of the choices of the FKs. They're fixed once and for all. Now, of course, you can say, what if I had made other choices? You can show that whatever you did there would work here equally well. So that's the fixed structure, and we're using it, and the use is hidden in this map that we have over here. That's our collection of choices packaged together into a single map. And what we're saying is that so the combination of the structure that we're given and specific choices related to the question that we have give us this the higher invariance. And that's, so it's complicated, but at least it's something manageable, and we see how we can use it for a simple purpose like that. Now, what I thought I would do, I hope I can manage to squeeze it in, is explain how what we can do for something maybe a little more interesting is how this is related to the atom spectral sequence. So it turns out that you can actually calculate the differential, well, you can describe the differentials in the atom spectral sequence in this kind of language, but it's a little messy, so let me talk about something else, which is the atoms filtration. So unstable atoms filtration. How do we figure that out using the structure that we have here? So let's think a minute what we're talking about. We claim that we have this tower of fibrations, which looks like this. So if we're careful, we see that what we have is we have a homotopy equivalence, and in fact a fibration homotopy equivalence to this thing that I was calling W dot before I made this read cofibrant. And then I have the map down, which is the real map in the tower, which is an actual fibration going to here, which is not, of course, a weak moment. So what you're actually patching together is cofibration sequences for in which you slightly have to change the spaces. Okay, that's just a technical point. But the nice thing about it is that this fibration sequence, you could identify the fiber explicitly. So remember, of course, we're not talking about the spectral sequence for the cosimplicial spaces. We're saying what happens after we apply towed to all this. So these are just ordinary spaces here. And our assumptions are that we've set things up so that this converges. That's why I said let's assume it's P good and finite type, and we don't have to worry about that. So now I have a spectral sequence in which we have a tower of fibrations in which we secretly squeeze this in between, and we're trying to, and at the top of the tower we simply get the tote, which is the P completion. And remember, what does it mean to say that we're in a certain atom filtration? It simply means that we start off with something in tote at the top, we push it down, and we see the lowest point at which it's still non-zero. Okay, but what we just saw here tells us that I don't have, right, so that's the usual way we think of tote as a homotopy limit. On the other hand, tote and y are not only have the same cohomology, but they actually have, they're P equivalent. There's a map from one to another. So we know that these obstructions are going to vanish if we apply them to z equals the completion of y, which is the tote. So the tote actually co-augments into the tower that we've chosen here at the bottom, which is kind of unusual, but we can choose a co-augmentation from it into the tower at the bottom. What does that mean? That means that, remember, I guess, for those of you who are not familiar with tote, I'll draw a picture in a minute, but usually it's quite messy to describe an element in tote. But in this case, we simply have a map. Let's say we have a map from SK into Y. I can continue it if you'd like into it, or I can just think of it as a map into Y. It doesn't matter if I think of it as an element in the P completion or just in Y. And I simply can co-augment this into W0 and then push it up all the way up. So its description in each one, and right, for each one of these, it doesn't matter what the n is, we have a co-augmentation into here. So I can push the map in from the bottom, and therefore it has a relatively simple description. Why does this help us? Because it's easier to think of this reverse process. So now instead of having something coming down from heaven and landing at some point here in level n, we have something that I'm pushing, I can push up all the way from below the map itself, but I have to choose a null homotopy for it. So now I have a lifting problem, which is how to lift a given null homotopy to the next level up. So let me just draw that picture. I think it's kind of cute in a way, but okay. So now we have to, but the homotopies is no longer true. They're not homotopies down below, or we'd be done. They're null homotopies that only are into the some level in the tote tower. So what does that look like? Okay, let's see what we have. We have at each stage, so I'll just draw in dimension a minus 1 of n minus 1. And here I have cross some contractible space, whatever dimension it is, n minus k I think, doesn't matter, wy and whatever we said back there, n minus k minus 1. No, n minus k, thank you. Okay, and at the next level up, I have wk of n minus 1, and here I have one less loops. And here I have this map going across, this map up, and here I have the various coface maps that I had before. Now, what do we have on the other side? Here, let's say, okay, so I'm being specifically talking about SK. Of course, I could do it for any space mapping in. Spheres don't have any special role here, but let's say that just to be specific, I'll call it SL, so it doesn't confuse us with these various things. Okay, so what do we have? An element of tote, if you have to think of it as we have a map into the bottom, we push that up along the edges, and then we choose homotopies between the various values of the coface. Of what happens at the corners. So what we get in the end in dimension k minus 1, we're supposed to get this, I'll just write it this way, mapping into here, where this map just projects off, because remember, this map we didn't need to choose all those null homotopies. The map itself is just the map from the sphere going all the way up along through the augmentation all the way up. So here we have a map which just projects onto SL and is well defined into here and into here by assumption. And now we want to choose a null homotopy for that. So if you think about this and check that these things are pointed, you actually get something which is the cone on the smash of the k minus 1 simplex with SL. Okay, we'll just take a minute. And now I have a map. Here, by induction, I have a map gk minus 1. So this is the null homotopy into the old part, which we're assuming exists. And what I'm trying to come up with is an extension of that into here. So I'll call that, let's say, hk minus 1. And then you go up, the next one up. It goes at this level, we get a map from delta k cross SL into here. And here we get a map from delta k smash SL. So this is an inclusion into here. And we have the GK, and we want to have this map HK. OK, I guess I have a minute, but that should be enough to at least give you an idea of what we want to do now. OK, so you see we're combining maps from different dimensional simplices into the part that's relevant is the part into these path spaces. Right? And if you look, here we have one path dimension. We have n minus k loop directions, so n minus k plus 1. And here we have another k minus 1. And we have a cone direction. So altogether, we have n plus 1 dimensions. If you adjoint this over, you get, instead of these maps hk, you'll get maps I can call hk minus 1. And they'll all be from the n plus 1 simplex into w bar n itself, because I've adjointed all this part over into the co-simplicial direction. OK, now I'll just try to, since I really just have a minute, I'll just try to give you a picture of what would happen at the very bottom dimension when I adjoint these over. And now I have to, of course, they have to fit together along the simplicial identities, right? That's part of what happens here. So here I have when k equals, let's take n equals 2. So the n plus 1 simplex is a 3 simplex. I'll just draw the boundary of it. And I have them for k equals 2, for k equals 1, and for k equals 0. And it turns out that what I have here is something that depends on h1, but that will also appear here, because on the one hand, the h1, I can restrict it along a face map. On the other hand, if I take if you understand what we mean by the path evaluation, which is one of these things appearing over here, you'll get it appearing in two spots. It's a little sketchy, but I just want you. OK, I'll be done in just 1 second. So here I get the same thing here over here, and what I have left over is simply the map f minus 1, f1 g1, f0 g0, and f minus 1, which is the map into here, composed with the original map G. OK, so what do? I now glue these simplices together. I get topologically an n plus 1 ball, but this identification means I just glue them along these simplices, and now I'm left with something which on the boundary depends only on these maps F0, G0, F1, G1, and the F minus 1, G. So that is a map from the boundary of an n plus 1 sphere, in other words, an n sphere. And what we're getting here is a nth order cohomology operation associated to G. And if that doesn't vanish, then I've produced an element that's an obstruction to lifting up the null homotopy to the next level up. So this is the meaning of the Adams filtration in this unstable world, which I guess we all know as a slogan, but here we can see it explicitly. There is associated to our G a higher, so basically the filtration says what's the longest cohomology operation, higher cohomology operation, that starts with the given map G, and the rest is maps between unbounded plane spaces that's non-zero in Y. That construction is that construction is exactly what determines the Adams filtration. Okay, so I think I'll end here. You mean like trying to realize, say, an algebra over the sphenoid algebra? Or yeah. Yeah, you can actually extract from this a lot of things. Right, so that was the thing that I'm connecting to stuff that Paul has done. So there is a version of that, and again, you get obstructions which you can interpret in this way. Of course, in some cases we have also more algebraic interpretations, but yeah, you can get an obstruction theory like that.
Other question? All right, let's thank David again.